Thank you very much for the introduction. And yes, as announced, I will talk about robustness for matrix-variate data. But in the beginning, I will start with a short introduction for the multivariate framework. And in the second chapter, I will talk about interpretability. So there we want to find out why is an observation outlying. The easy answer for this might be its Mahalanobis distance is too large. It's above a certain cutoff from a chi-square quantile, and thus we consider it as an outlier. But in the multivariate context, it's often very interesting which variables are responsible for the outlyingness. And this is what we will look at in the first part. In the multivariate setting, we already have robust estimators for location and covariance. In the matrix-variate setting, this is a new development, and I will talk about how we can generalize the MCD, the minimum covariance determinant estimator, from the multivariate to the matrix-variate setting. And if there is time, I will also talk about a generalization from the one population case to the multiple population case. So I will go from simple mean and covariance estimation with outlier detection to robust clustering, where we just have multiple means, multiple covariance matrices that we want to estimate. And we do this also in a trimming framework. So some of the observations can be outliers and we can deal with them. So in recent years, data collection tools have increased in their power immensely. So we are more and more faced with higher complexities in our data. And a very common example here are multivariate data, matrix-variate data, or also functional data. And here we will focus on matrix-variate data. And of course, in real data sets, we often face outliers. What is an outlier? In this context here, an outlier is an observation that is deviating from the majority of our data set. So in robustness, we're interested in fitting the majority of our data, so at least 50%. We are assuming that those 50% or more of the data are from the same distribution, behave similarly, and some outliers can behave differently, and we do not assume anything on how the outliers behave, if it's a cluster, if they're spread out over a random error domain, if they are created by several other random distributions, we don't assume anything about it. And beyond detecting the outliers, we want to explain the reasons for outlyingness, and this can reveal interesting patterns in our data. So the first motivation I want to start with is, why do we need robustness? So here we have a simple two-dimensional example, an X and a Y, and we can estimate the covariance, which is represented here by the black ellipse. If we add a small outlying cluster to this population, then the sample covariance would be represented here by this orange ellipse. If we would then use the standard tool for outlier detection, which is the squared Mahalanobis distance, then we would see something like that. This here is the chi-square cutoff, which is usually used to infer whether an observation is outlying or not. And then all the orange observations would not be marked as outlying, which is, in the sense of robustness that we consider here, not what we want. We want to find the best estimation of the majority of the data. And a good way to do this is the minimum covariance determinant estimator. The goal of this estimator is to find a subset within your data. So you have n observations, and you want to find a subset of size h, where h is more than half of your data, whose covariance matrix has the smallest determinant. So in 2 dimensions, you're basically investing all possible subsets if you would compute it brute force, and then you would keep the covariance matrix, which has the smallest area. If we compute this estimator for this example and compute the Mahalanobis distance based on the robust estimators, then we can clearly distinguish between the outliers and the regular observations. Now moving to a more interesting setting where we no longer only consider 2 dimensions, but more dimensions. The MCD estimator still works there, but here it is rather easy to see whether an observation is outlying because of its deviance in X or because of its deviance in Y. But this is harder to see in higher dimensions. And especially also the multivariate outlying estimators are what are very interesting there. So in this work, we created an approach on how we can analyze the reasons for outlyingness. And what we use there is the Shapley value. The Shapley value is a concept from cooperative game theory, and it provides a fair payoff distribution. So in cooperative game theory, you have a set of players. They work together to create a profit. And the Shapley value tells you, how do I fairly distribute this payoff between our players? What we have here is we have a squared Mahalanobis distance, and we want to fairly attribute each variable its contribution to the Mahalanobis distance. That's the idea. And Shapley values have been very popular in explainable AI. In this paper from 2017, last time I checked, it was about 30,000 citations. So this gained a lot of notoriety in this field. And as I said, we have incorporated game theory, we have a set of players, we have a coalition. A coalition is every possible subset of the set of players, and we have a payoff function. This assigns to each coalition some payoff. And the Shapley value is then a fair payoff distribution. It basically checks for each possible coalition with and without the JS player, how does the payoff change? And this assigns each player its average marginal contribution. This is what is written in this formula. And we want to use it to decompose the squared Mahalanobis distance. And our set of players here are our P variables. A coalition is the same as before, so we have a subset of our variables. And the payoff function is the squared Mahalanobis distance of our observation. But it is a modified version of our observation depending on the subset of variables. So if a variable here is within the subset, then it keeps its original value. And if it is not, it is replaced by its expectation, unconditional expectation by its mean. This is something where we could think about extending this concept. We could here use the conditional expectation. We've tried it, but we could not make the same generalizations that I will present later on, which is why we here choose the mean. What we can do then is we decompose the squared Mahalanobis distance, we plug in the definition, all the things we need, we have there, and then we can compute this. But as you can see here, we would have to go through all possible combinations of variables. When I started, I implemented this brute force. It worked till p is equal to 10 maybe. Then it stopped working, but till p equal 10, the results were quite nice, were what we expected them to be. And what we have shown is that we can actually very much simplify this expression. We can simplify it to this equation 2 here. And if you look at this, then you actually get, if you look at the all component-wise contributions assigned by the Shapley value, so this is the phi j here, and if you sum about over all of them, then you get the squared Mahalanobis distance. So what we have here is all possible combinations of variables, and we weight them, we average them, and we can simplify it to this simple formula where this omega here is the an entry of the precision matrix, so of the inverse of the covariance matrix. And it is an additive decomposition, so we can just sum up the outliers contributions, and we get the squared Mahalanobis distance. How do we interpret this? So a positive value of phi j indicates that replacing xj by mu j, so replacing the variable by its mean, would lead to an average reduction in the Mahalanobis distance, and the other way around for negative values. The additivity here is not by chance. The additivity is a property of the Shapley value, but it makes a very neat equation here that we know. It's just a formula for the squared Mahalanobis distance. And what is very nice here is we can reduce the computational complexity from exponential complexity in the number of variables to a linear computation complexity. A simple example to illustrate this is based on the Top Gear dataset. There, from the television show Top Gear, they test some cars, and there's an online database where they collect the characteristics of all the cars. This is already an older version of this dataset, but it has around 250 observations, and 11 numerical attributes are recorded in there. We use the MCD estimator to get the robust location and covariance estimate, and we then find about 80 outliers. This is what the observations with the robust Mahalanobis distances look like. And we now want to look at 3 of the outliers and understand the reasons for the outlierness. So what cars I chose here are the BMW i3, that's the most outlying observation. The Bugatti Veyron, this is a very special car, very expensive, very fast. And the SsangYong Roidus. I should really start including here pictures of the cars, because the BMW i3 is a hybrid car, so we can maybe imagine that it is different than most of the other cars, which are just gasoline or diesel. And the SsangYong Roidus is a minivan. It's not special at all, so why is it different in this sense of the dataset? That's what we're going to find out. So here are the squared Mahalanobis distances plotted, and here are the decompositions of the squared Mahalanobis distances. And as we can see here, for the BMW i3, it's mostly outlying due to its miles per gallon variable. So it is a hybrid car. It also runs on battery power, has an electric motor, and this is not accounted for in the miles per gallon variable. So it runs, it just needs way less fuel than the other cars in the dataset. And actually, the other 2 most outlying cars, so the top 3 of the most outlying cars, are the 3 hybrid vehicles in this dataset. Since we don't want to see for each outlier the same explanation, we can also look at the Bugatti Veyron. This is also high outlyingness, but it's, as I said, it's a super sports car, and it is mostly outlying due to its price and to, for example, top speed and torque. And then we have our family car, our minivan, and this is outlying due to its acceleration. And I checked in the dataset, and its acceleration is 0 to 100 in 0 seconds. This is, of course, a mistake in the dataset, and we can find it in this way. Probably it was a missing value, just imputed by 0 by default. And we can now move on to a higher complexity of the observations. So now, instead of considering only vectors as observations, we consider matrices as observations. So the example I will use here are video data. Here, each frame is considered as an observation. And we will look at this example later on, where we have around 600 frames. 450 of them are without much going on. And then there walks a man through the scene, through the static image. And these are the observations that we would then like to identify as outliers. So what we had before is multivariate data. Multivariate data are usually arranged in a data matrix. So we have n observations with p variables, and this is collected in an n times p data matrix. For matrix-variate data, we get a data tensor. Each observation is a matrix with p rows and q columns. And we then have a 3-dimensional tensor with these n observations. And a common example are image data, but also panel and longitudinal data, multivariate functional data. So for functional data analysis, you cannot record functions on an infinite dimensional domain, but you record them at finite time points. And if you record them at finite time points, they are again matrix-valued observations. And also spatio-temporal data are often modeled in this framework. What our goal is here is also interpretable outlier detection. Before, we already had the covariance estimation procedure available, the MCD. Here, there is no such robust version available, so we developed our own. And then we can explain the outliers again using Shapley values. So the simplest approach to model matrix-variate data is just vectorization. So we have a matrix, we just stuff it into a long vector, use multivariate or regularized versions, and we are done. However, with increasing dimensions, there appear problems. So for example, if you want to estimate the mean and the covariance matrix, and you vectorize a 250 times 250 grayscale image, you end up with a 60,000 times 60,000 dimensional covariance matrix. And on my laptop, I could not even store the covariance matrix. I couldn't, of course, I can't compute it, but I couldn't even store it because I have too low RAM. So you can maybe use this in certain settings, the vectorization, but for many practical applications, you will run out of memory or computational time. Our approach is to model it using random matrices. And there is the family of matrix-variate distributions. This is a generalization from the multivariate distributions. And we say that the random matrix here follows a matrix-variate normal distribution where it has a mean matrix, a row-wise covariance, and a column-wise covariance. If and only if its vectorized version has a multivariate normal distribution with the separable covariance structure here. So what are we doing? Here we are actually reducing the amount or the number of parameters that we have to estimate drastically. Here we would have a PQ times PQ dimensional covariance matrix. Here we estimate a P times P dimensional covariance and the Q times Q dimensional covariance, which saves us very, very many parameters. And for estimating them, if we choose the matrix-variate normal framework to motivate our estimators, which is what we did, we can compute the maximum likelihood estimators. The sample mean is just the maximum likelihood estimator for the mean matrix. And then we get equations 4 and 5 for the row and column-wise covariances. And those are always depending on the inverse of the other matrix. So for the row-wise covariance, I need the inverse of the column-wise covariance. This means I cannot explicitly compute them, but I can iterate between estimating one and the other and initialize this procedure simply by the identity matrix. And after a few iterations, usually we already converge. And maybe just for intuition, what is it what we are doing here? Basically, when we estimate the dependency between the row, we standardize our observations between the columns. And then if you would call this xi minus mu standardized for the columns here, if you would just call this set, then this is just a sample covariance for the transformed observations. So it is actually very logical what we do here. We are just taking out the dependency structure with respect to the columns if we estimate the row covariance, and vice versa for the column covariance. And the iterative algorithm for computation here converges relatively quickly, usually 3 to 5 iterations, and we already converge. And even if we would not include these inverses here, then we would get just the moment estimators. The moment estimators for extremely high dimensions are almost exactly equal to the maximum likelihood estimators, but they just require a much higher sample size to be efficient. So for small sample sizes, actually using this bit more of computational resources really pays off because we get way more efficient estimators. And the power here of this framework is really the required sample size. By having the separable covariance structure, we just drastically limit the amount of parameters we have to estimate. And then the existence of these estimators is already guaranteed if the number of observations is larger than this quantity here, so P over Q plus Q over P. And for example, for squared matrices, no matter of their size, they can be 2 times 2, they can be 500 times 500. You just need 4 observations for these estimators to exist, and they are unique up to scale, and you can compute them rather easily with very small sample sizes. And if you vectorize again, you would need just a lot more samples to actually get a positive definite covariance estimate. And for outlier detection in this setting, we can use the matrix Mahalanobis distance, which is also corresponding to the multivariate Mahalanobis distance with this Kronecker structure here. But of course, in the matrix-variate setting, we do not actually compute the Kronecker product, but we can use a more efficient formula to compute it. And in the multivariate setting, we had our MCD estimator. Now we also want a robust estimator in this frame. Our approach here was to motivate this with a trimmed maximum likelihood framework. So we just compute the maximum likelihood estimators, but we put here weights, which are either 0 or 1. And we want exactly age of the weights to be 1. And this is already hopefully reminding you of the MCD framework. And one can actually show that you can write the MCD estimate and the multivariate framework as a trimmed maximum likelihood estimator. And this is also what we did here. We wrote it as a trimmed maximum likelihood estimator. And then we have our 0, 1 weights here. And we can show that maximizing this expression is equivalent to minimizing this expression, which is just the determinant of the covariance matrices. And here, we don't have to compute the Kronecker product, but we can use just the rules for the determinant applied to a Kronecker product, and we get a very simple expression. And with this at hand, we can then design a very quick algorithm. So because for the MCD estimator, a crucial point is how to efficiently compute it. It has been around quite a time longer. I think it has been developed in '85 by Peter Roseo. And it only was then used starting from the 2000s, because then is when a fast estimator got out, a fast algorithm to actually compute it. And the challenge here was to also find a way to compute the estimator, but we have our flip-flop algorithm to compute the maximum likelihood estimators for the covariance matrices. And those, of course, increase the likelihood. And since this, we have this connection between the determinants here and the likelihood, we can also use the same C-step procedure we use for the MCD here in the Matrix-variate framework. And this is the definition for our estimator. So this is the Matrix Minimum Covariance Determinant estimator. And we are looking for row-wise and column-wise covariance matrices. And we are looking for the subset of the observations that give us the smallest possible covariance determinant. And again, here, this is just translated then to the trimmed setting. The existence of these estimators, again, depends on this quantity here. And now our H subset needs to have at least this amount of samples, which is then also very convenient. So we can get robust parameter estimations with very high robustness guarantees for sample sizes of 6 or 7 observations. So then we can already start to distinguish between observations that are more similar and that are quite different from each other. Another property of the matrix minimum covariance determinant estimator is its matrix affine equivariance. I wrote down here what this means. And what was quite interesting for us when we looked at this was we derived the breakdown point for this estimator, and then we saw that it has a higher breakdown point than the MCD estimator. And the MCD estimator, if you know, it is the most robust estimator that is affine equivariant that you can get. So we were a bit worried because we had a higher breakdown point. And we had this matrix affine equivariance property. But then we have seen that this matrix affine equivariance, of course, does not imply affine equivariance of the vectorized samples. And then we were more confident that our theory is actually correct and that we actually have these advantages in breakdown point. And this is what I want to illustrate here. So for here, we just chose 5 times 20 dimensional matrices, so not too high dimensional, but already quite something that we can save by using our framework. And the orange line here represents the multivariate version of the MCD, and the blue line is the matrix-variate version of the MCD. And the breakdown point tells you how many observations in your data set can be outliers without your estimator breaking down. And you can see here for the vectorized versions, you have a quite low breakdown point for quite a bit of quite a large sample size. So still for 200 samples, you have a breakdown point of, I don't know, 20–25%. And its asymptotic breakdown point is a half. So you need quite a high sample size to reach this. And for the matrix-variate estimator, you are very quickly increasing to the 0.5 benchmark. We have also shown that the estimator is consistent for all elliptical distributions. So in the multivariate framework, we have the family of elliptical distributions, and this family can also be translated to the matrix-variate setting. And we also get consistency in this framework. But this all, of course, as in the multivariate framework, has to be taken with a grain of salt. So we get consistency, but we have here a consistency factor. And this consistency factor, of course, depends on the distribution. And we always choose this consistency factor to be consistent under the matrix normal distribution or multivariate normal distribution. And this consistency factor is not estimated from the data, but it is computed in advance, just applied here, and then you get consistency for the matrix normal distribution. But if you would know that if you want to apply this to a t-distribution, you can compute this for the t-distribution and just plug it in as well. But by default, it's always for the matrix normal. What we have also developed is a reweighting step. So to have in robustness, you always have this trade-off between efficiency and robustness. So if you have a very efficient estimator, you are using all of your information very well to get a good estimate. If you have a very robust estimator, you try to exclude as many observations as possible that could potentially be outliers. And for the MCD estimator, you usually try to make this as robust as possible. So you exclude half of your observations and you just keep those half of your observations that are most similar to each other. But if you actually have no outliers in your data set, then you're just wasting half of your observations to get a way less efficient estimator. And this is where re-rating comes in. And you can do this by just one additional step, and you increase the efficiency of the estimator quite a bit. And we have also developed a fast algorithm to compute the estimators. This is also inspired by the multivariate procedure. And we then also generalize the outlier explanations I've shown you before, where we can now get cell-wise attributions for each cell in the matrix, or we can aggregate them for the rows and the columns. So this is quite nice when you think, for example, of outliers in the variables that are recorded over time. So you might not be interested, was it too hot in March in just for the temperature, but you might also just be interested in, was it too hot? Then you aggregate the outliers just for the rows, for example. If you have in the rows, you have the different temperature, precipitation, and so on. And over the columns, you spread your time. And then you can actually accumulate all these outlier scores either for the time points or for the different variables, which allows you to get also interpretability if your dimensions grow both in the rows and the columns. And of course, we can apply it to the video example I showed you in the beginning. This is what we did. We converted this into a grayscale image. Here it's still shown in RGB. And then we found some of the outlying frames. And we computed the cell-wise Shapley values, which then show you which pixels contribute most to the outlierness. And what is quite interesting here is you see that it doesn't highlight the entire person with red pixels, but it focuses way more on the contours of the person. And this is all actually what we want if we also include the covariance in this outlier detection framework. If we would just look at the mean difference, then the entire person should be highlighted. This is outline. But what we see here is the contour of the person is where the covariance structure is hurt the most. So then the other pixels within the man, so of the body of the man, they are more closely related again. They're not that different from each other. And it also depends a lot on the background, which part is highlighted. So here, for example, in front of the grass, the trousers are way harder to detect than, for example, the head in front of the sky. We can look at this also over time, where we see that the Mahalanobis distance is actually quite useful. If the person disappears behind the tree, the Mahalanobis distance is decreasing. When he reappears again, it is increasing. And we can have here the outlierness contributions. But towards the end, you can also see some of the bias you introduce by regularizing your covariance with the separable structure, because video data in general won't be separable. You just have found a model that allows you to model the data, but a theoretical test for separability of video data will almost always be rejected. But still, it's one of the things you can do computationally rather cheaply. And what we have also shown with simulations is, even if you have non-separable data, the ranking provided by the Mahalanobis distance of the non-separable and the separable covariance is almost perfectly in agreeing. So if you do not create your data in a way to specifically only have differences in a non-separable setting, then this usually gives you very good results. And the last topic I want to touch upon is clustering for matrix-variate data. Here I again chose image data as examples because it's nice to illustrate. And these are data from the MNIST fashion data set. This has 10 clothing items, but I just chose 3 clothing items and tried to find outliers in this data set and also cluster them. So in robustness, one of the most well-known procedures for clustering is T-cluster. This is trimmed clustering. So there you are looking for mean vectors and covariance matrices, you are looking for weights that sum up to 1. Those are the partition sizes. And then you also have the partition. You have a partition into k groups, or k plus 1 if you include the trimming. In the R0 partition, you include the outliers. So this is the proportion of your data that you trim out from the clustering. And the other k members are the other k subsets of your partition that divide your data set into the groups. And in the matrix-variate setting, we are looking for the same thing, but now we are looking for mean matrices and row and column-wise covariance matrices. Here is the objective function if we want to have unbiased estimators. So here this gives us a biased approach. If we are, for example, interested in consistency, then usually we want to use the unbiased approach. This here is often called classification likelihood. And this here is the proper mixture distribution that we could also use in this framework. But what I did is, for the beginning, because this is still work in progress, is I stick here with equation 10, the classification likelihood, because it is computationally a bit simpler. And there are some non-robust procedures already available. So there is a finite mixture of matrix-variate normal distribution paper available. And there is also a proposal for regularized estimation here. And I was very much interested in regularization because when you are interested in clustering and especially in image data, you often have in your images, you have a certain row or column that is just of the same color all the time. If you then estimate a covariance matrix, then this covariance matrix will be singular because all the values within one row or one column have the same value. This happens all the time in the n-ness digits data set, for example. There you have black borders right next to your between your numbers, and then you have a problem with estimation. What they did here is they regularized the means. So they had the means converging to each other. So they have a pooled mean. They did not consider regularization of the covariance matrices, which is in this context very important. And what we can do here is we can regularize with respect to the maximum and minimum eigenvalues for your row and column-wise covariance matrices across all clusters. So basically what you're saying is the largest variability in your cluster and the smallest variability along one dimension in your clusters cannot be too different. What does this mean? In the two-dimensional case, you can think of it as you do not allow very spurious clusters. So if you would have one cluster that just includes two observations, and which would make a very, very narrow cluster, then you do not want this, but you only want to have somewhat similar clusters that express a similar amount of variability. And this similar amount of variability can here be controlled by this condition number constraints on the covariance matrices. And what we have then generalized here is this trim clustering approach that I've mentioned before. And a very big challenge in this trimmed clustering framework is initialization. So basically what you want to have to initialize your algorithm is enough samples to get positive definite covariance estimates in each group, and each group should be pure. So there shouldn't be any overlap between the partitions with different groups, and you also don't want any outliers in there. So what you would like to have is a subset of k for the number of clusters of k plus one dimensional subsets that are perfectly separated in this sense. And for the this data set, we would here need more than 2,000 samples to have this condition fulfilled. In the matrix-variate setting, we need 12. And as you can imagine, it is way simpler to find random 12 observations that are well separated than to find more than 2,000 observations that are well separated. And we can actually compute the probability. I don't want to go through the details here, but I want to illustrate the point. Here, this is the probability of obtaining one such a perfect partition. And you can see here for 5 subsets that we try to find these partitions for 50, for 500, or for 5,000. This probability of, so you want the probability of at least, let's say, 99% to obtain a clean partition at least once in your data, in your initialization of your algorithm. If you look at this here for even one cluster, it works very nicely. And if you have only one cluster, you're actually in the MCD case we had before. If you have multiple clusters here, then you are in the clustering setting. And this only works here for 2 observations. And if this set size increases, this gets very difficult. If you allow for some mistakes, this works better. And you can see, for example, here for the set size of 5 or 6, this is still reasonable and works in many cases. But for larger set sizes, it doesn't work. And this is something that they struggle a lot with in this robust trim clustering framework. Because if you have data sets that are 3-dimensional, then and many people question whether this method is so relevant or not. And if you can deal with settings where you allow for more variables, then you can create much more interesting problems. And by using this matrix-variate approach, we can save a lot of the parameters, which means that we need smaller sample sizes to initialize our clusters, and we have a higher chance of getting a good initialization. Here is what came out for one example here in the clustering framework for the endless fashion data. So we had a dress, we had sandals, and we had bags here in this example. And we get about 90% of accuracy, and we trim 10% of the observations. And this is again what the data looked like. And now we can again apply our explainability framework based on Shapley values. So this is the most outlying observation. This is the mean of class 1, class 2, and class 3. And now we can compute the Shapley values for each class. We see that for the dress class, we have a lot of very high outlierness contribution. So it's very unlikely that this dress will be classified as a dress. And why is this? Because its color is very different or not smooth. It is varying a lot. It has a different pattern than most dresses in this data set. And it also has sleeves, while all the other dresses here do not have sleeves. If we look at the bag, for example, in contrast, then at least the sleeves are no longer a problem. And it would actually be classified as misclassified as a bag here. But since we allow for trimming, then it is actually trimmed out of the data set. We can also look at as a misclassified sample. I think I do have here. So here I have a misclassified sample. So we have a dress assigned to class of the bags. And again, we can look at the Shapley values, and what we see here it is assigned as a bag, or it's classified as a bag because of the sleeves, because all the dresses that are in the dress group do not have sleeves. This explains the difference. And before I was just wondering, why doesn't it get it? It's so simple. It's completely obvious to see it, but for me at least, it was hard to find the pattern without any help. With this, it was immediately clear what is going wrong. So to summarize, what we discussed here is a framework for multivariate, matrix-variate, and here is still hidden the functional. I did not talk about that, but also for clustering data that have an inherent structure. It makes a lot of sense to account for that inherent structure to get advantages for computation and also for theoretical properties. Shapley values can help us to understand the results of an algorithm, here in this term for outlier detection, for explaining clustered assignments. With the MMCD estimators, so the Matrix Minimum Covariance Determinant estimators, we have a framework with nice theoretical properties that allow us to robustly estimate covariance and location for matrix-variate observations. And we have an efficient algorithm to compute it. And we can do robust clustering for matrix-variate data by generalizing the MMCD approach to the trend clustering approach. And Shapley values, again, here are used to explain differences between clusters or also explain outliers. All the methods for outlier interpretability are available in the Shapley outlier package, which is on Khan. And for matrix-variate covariance estimation, there is the robust matrix package, which is also available on Khan. And maybe some paths for future research that we're considering or that are also still completely open is here. For explainability, this is what I mentioned here. One could switch from replacing variables by their mean to find outlierness by replacing it with their conditional mean. In my opinion, the biggest advantage of this would be we can only get positive scores then for Shapley values, because the negative scores for outlierness contributions are actually kind of annoying. It is hard to interpret. We have verified via simulations that high scores correspond to high contributions, so they do work, but it would just be way more intuitive to only have positive outlierness contributions. And this could be achieved by using the conditional expectation. And I've tried quite a bit to find then a simplification from this exponential computational complexity, but I could not manage it. So if you have any idea or want to try it yourself, please feel free. This would make a very, very nice contribution, I think. For matrix-variate data, we can go from matrices are 2D tensors, we can go to higher dimensional tensors, and higher dimensional extensions for the MCD we have already started. So we had a master's thesis which considered three-dimensional tensors. So for example, we considered the same video data, but in color, or we considered video sequences as the third dimension. And one could extend it also to cell-wise robustness. So what we did here is we were looking for entire observations that are different from the majority. But you could also just look for single cells which are different, and then just replace those cells with values that are better fitting to the data set. And then you would not have to discard entire observations. So this would be a more responsible way of handling your data, but it's computationally very, very expensive. Another thing is getting robust tests for separability. So this is something we have published the MMCD paper in Technometrics. There we got the question, can we test for separability? The answer is yes, but if the test is not robust, you do not know if it is rejecting separability because of your outliers, because a single outlier will destroy a non-robust separability test also for separable data very quickly. And you do then simply, you don't know. And this is something we're also currently working on, and we are already having some very promising results there. And the next step would be to move beyond separability. So separability allows you to get robustness for small sample sizes. This is very nice. But in practice, actual separability is not so common. So it would be nice to maybe start with the separable framework, get a robust subset, and then use a method that goes beyond separability to refine your results that you got. And for multivariate functional data, we can show that we can use our framework, And a new student in our department is now looking at random surfaces. So basically data that are smooth in both dimensions, or if you think further, you can have a mixture of smooth dimensions and discrete dimensions, and you can go higher dimensional. So again, the tensor framework, if you think of this, you can have arbitrary dimensions, and some of them can be smooth, some of them can be not smooth. And this is a very interesting setting to consider. Here are some of the references. And with this, I want to thank you for your attention. And please do not hesitate to ask any questions, and maybe I'm even able to answer some of them.